Okay, our third and final example. Here we're going to find the area of the largest isosceles triangle that can be inscribed in a circle of radius 6. And it's broken up into two parts. We're going to solve by writing area as a function of h, and we're going to solve by writing area as a function of alpha. H is this line segment here, and alpha is this angle right here. And so h can shrink to 0, and it can be up to 6. If it's 6, then our isosceles triangle will just be a diameter. So that defines our valid domain for this particular problem, even though we might have a few issues. So the first thing we want to talk about is area of a triangle. Remember, it's 1/2 base times height. And so first off, we're going to talk about this triangle. And just for the sake of keeping my numbers nice and easy, I'm going to call this h the distance here, not the total height. And I'm going to call 1/2 of each of these b. So I'm going to call that b, and I'm going to call that b, so that when I say half of b, I'm only talking about this thing, and that'll keep my numbers just a little bit easier. So if I want to find the area of this triangle, it's going to be a is equal to 1/2 this whole length, which is b, times the height, which is going to be 6 plus h. Now, here again, I have an equation in two variables. I don't have any additional information to make a secondary equation, but I do have this right triangle right here that is defined in h and b. So what I can do is I can solve for b in terms of h and this 6. And since this is a height here, we know that that's a right angle. So I can say that b squared plus h squared is equal to 6 squared. And since I want to get rid of the b value, and I want to have just in terms of h, I can rewrite this as b is equal to the square root of 36 minus h squared. If I subtract h from both sides, I square the 6, and then I take the square root of that. Now I can plug this back into the a equation and now say that this is 36 minus h squared to the 1/2 power, converting the square root into the 1/2 power, times 6 plus h. This part is now good because I now have an equation for the area, which is what we're trying to solve for area, in terms of h only. And if I go to derive this, I'm going to have to derive this with both the product rule and the chain rule. I've got a product between 36 minus h squared to the 1/2 times 6 plus h, and then I have a chain in this first function. So a prime is going to equal, I'm going to leave this first function alone, and so it'll be 36 minus h squared to the 1/2. And then times the derivative of the second. Well, the derivative of 6 plus h is easy, it's just 1. Plus, now I have to derive this second function, but it is a composition of the square root function and the 36 minus h squared function, so I have to do a chain. So I bring the 1/2 down in front, I leave what's inside alone, 36 minus h squared, and then I reduce this 1/2 by 1, that'll give me negative 1/2. I then have to multiply by the derivative of what's inside, which will be negative 2h, and then I have to multiply this derivative by the second function left alone, so 6 plus h. Alright, so now I need to simplify a little bit. Multiplying by 1 just means that it stays the same. And this negative is going to change the plus to a minus. The 2 and the 1/2 will cancel out. And so I have on the top this h times 6 plus h. And this 36 minus h squared to the negative 1/2 will go to the bottom. And the negative exponent will change to a positive. So I have 36 minus h squared, all to the 1/2 power. All right. So now if I want to get this into a single fraction, I have to multiply by a funky 1. And that funky 1 is going to be 36 minus h squared to the 1/2 all over 36 minus h to the 1/2. And when I do that, the halves will cancel out. And what I'll have is I'll have 36 minus h squared now to the first power, and then minus, I'm going to distribute this negative to these two terms, so I'll have negative 6h and then minus h squared, and then that will stay all over 36 minus h squared all to the 1/2 power. All right, so we're still simplifying. We're going to collect some like terms here, and I end up with a prime equaling negative 2h squared minus 6h plus 36 all over 36 minus 2h squared to the 1/2. And I can divide out a negative 2 from each of these terms, so we'll leave it at a prime is equal to negative 2 times h squared plus 3h, and then it'll be minus 18 all over 36 minus h squared. So I need to find my critical numbers. Well, both 6 and negative 6 make this undefined. And then if I factor here on top, so let's say I factor this expression here, h squared plus 3h minus 18, that thing factors, two factors of 18, two factors of negative 18 that add up to 3, x plus 6, and then x minus 3. And that gives me the critical number negative 6, which I already have, and then positive 3. And so I note both 6 and negative 6. Now let's go back up to the original problem. If I let h equal 6, because the radius of the circle is 6, if I let h be 6, it'll go all the way down to the bottom, and I will have an area of 0 because essentially these two sides will become diameters. Now if I let h equal negative 6, it will go all the way back up to here, and again I'll have 0 area because I will have no length in my triangle. So both 6 and negative 6 make the area equal to 0. Thus, h equal to 3 will maximize the area. Okay, so if h equals to 3 maximizes the area, it says find the largest area. So we actually got to find that. So here is my area equation. So what I'm going to do is I'm just going to plug 3 in for h. So my area equation is going to be 36 minus 3 squared to the 1/2 power times the quantity 6 plus 3. That'll give me, well, 36 minus 9 is 27. So I'll have 27 to the 1/2 power times 9. If I take 27 to the 1/2 power, let's go over to here and say square root 27. Well, 27 is the same as 9 times 3, which is 3 square root of 3. So if I go 3 square root of 3 times 9, I will get a maximum area of 27 square root of 3. And let's check our units. Do we have any units? We have no units, so we'll just call it units squared. All right, part B. In part B, we're asked to solve by writing the area as a function of alpha. All right, so let's copy back this. Let's redraw that triangle. And so we'll have here is my alpha. This was 6. This was h. This was b. This is also 6. And we can rewrite this b as the square root of 36 minus h squared. We're going to throw in an n here for this right triangle. Now, n is going to be the hypotenuse of a right triangle that has one side, 6 plus h, and then the other side will be the square root of 36 minus h squared. So let's write that out. Let's say that n squared will be equal to 6 plus h quantity squared plus the square root of 36 minus h squared quantity squared. All right, so I've got n squared. I've got to multiply this out. It'll be 36 plus 12h plus h squared. Now, the square root and the square cancel out, so we can just say that this is plus 36 minus h squared. Now, the good news is that for n squared, 36 and 36, that's just going to give me 72 plus 12h, and then this positive h squared and this negative h squared will cancel out. So n is just equal to the square root of 72 plus 12h, and I can factor a 12 out of each term and say that that is the square root of 12 times 6 plus h, and then 12 cancels down to 2 square root of 3 times the square root of 6 plus h. So my n here is going to be 2 square root of 3 square root of 6 plus h. All right, now why did I go to do that? Well, let's go back to the question again. And the question says solve by writing area as a function of alpha. So I need to reduce all of these h's out and change them to alphas. And the way that I'm going to do that is by using cosine and tangent. And if you remember, cosine of alpha is going to equal the adjacent side over the hypotenuse. And so in this particular instance, the cosine of alpha will equal the adjacent side, 6 plus h, over the hypotenuse, which is 2 square root of 3 times the square root of 6 plus h. This can be rewritten as 6 plus h to the first over 2 square root of 3 times 6 plus h to the 1/2. Now, if you remember, I have two exponential expressions with the same base, 6 plus h. So I can subtract these exponents and rewrite this as 6 plus h to the 1/2 over 2 square root of 3. And that's my cosine of alpha. And then I can solve this thing for h by multiplying both sides by 2 square root of 3. So I'll have 2 square root of 3 times the cosine of alpha equals 6 plus h to the 1/2. I can square both sides and get 6 plus h equals, well, we already know what 2 square root of 3 squared is. It's going to be 12. Cosine squared alpha. Now, why am I leaving this 6 plus h alone? Because I'm going to plug it in eventually somewhere else. I can come back up to here and again rewrite. Now again, I'm trying to cancel out my h's, so I need a second version of this expression with alpha in it. So I'm going to choose tangent. I'm going to say that the tangent of alpha is equal to the opposite side over the adjacent side. And that will give me the tangent of alpha is equal to, the opposite side is the square root of 36 minus h squared, and then my adjacent side is just this side here again, which is 6 plus h. And so now I can say that if I multiply both sides by 6 plus h, I can say 6 plus h times the tangent of alpha is equal to the square root of 36 minus h squared. All right, so why did I do all of that work? Let's go back to part A. Now, in part A, I have this expression right here. So I'm going to select this expression, and I'm going to copy it. I'm going to come back down here, and I am going to paste this right here. So now I did all this work with cosine and tangent so that I could replace these values with the expressions you see here and here. So I can replace this 36 minus h squared with this expression here, a equal to 6 plus h times the tangent of alpha. And then I can replace this 6 plus h with 12 times the cosine squared of alpha. Now again, that's not 100% perfect because I still have h in it, but it's another 6 plus h. So I can take this 6 plus h right here and replace again with 6 plus h. So I'll have a equals 12 cosine squared alpha tangent alpha times 12 cosine squared alpha. Now this can be simplified down to a equal to 144 cosine to the fourth alpha tangent alpha. So now I have area in terms of alpha only. And again, that was a lot of work, but I have done what the question asks. Solve by writing area as a function of alpha. That is what I have right here. So now I can do the derivative of this. Now I want to derive this, but I'm going to leave this 144 out in front and just using the constant multiple rule so I don't have this big 144 out there. So I'm going to leave this expression alone, so it'll be cosine to the fourth alpha, and then the derivative of tangent is secant squared alpha. And then to that I'm going to add, and now I got to do the derivative of this, so it'll be 4 cosine, and then I've got to reduce that by 1, so it'll be 3, and then it'll be of alpha, and then I have to take the derivative of cosine because it's a composition, and so the derivative of cosine alpha is the negative the sine of alpha, and then I have to leave the tangent alpha alone. Okay. So again, let's simplify a little bit here. Got 144, and then it'll be cosine to the fourth alpha, and then secant is 1 over cosine. So secant squared alpha will be 1 over cosine squared alpha. Then I'll move this negative out and make it a negative, and I'll have 4 cosine to the third alpha times the sine of alpha times, now tangent is just sine alpha over cosine alpha, and so 144 stays, and then both cosines in the bottom cancel with 2 of the cosines in the top, so I have cosine squared alpha minus 1 of the cosines cancel with the cosine in the bottom there, so squared, so I have minus 4 cosine squared alpha sine squared alpha. And remember what we're trying to do. This is a first derivative, so I want to find a maximum or minimum, so I have to set it equal to 0. So if I set this thing equal to 0, I'll have 144. Now I have a cosine squared and a cosine squared, so I'm going to factor that out, and I'm going to say it's cosine squared alpha times 1 minus 4 sine squared alpha. And we're going to set both of these equal to 0. So when I set this part equal to 0, the 144 becomes irrelevant. I just have to go cosine squared alpha equal to 0. And I didn't need this, so we'll erase it. And then 1 minus 4 sine squared alpha equal to 0. All right, so I need to know where cosine squared alpha is equal to 0. Well, cosine is equal to 0. Because I take the square root of 0, I get 0. So alpha, cosine is equal to 0 at pi over 2 and 3 pi over 2. Now, if we go back up to here, at pi over 2, we'll have a right angle. And at 3 pi over 2, it'll go all the way around. That's going to be far too big, so we've got to throw these two out. They don't make sense. Now, if I set this equal to 0, I can say that the sine squared of alpha is equal to, I will subtract 1 and divide by negative 4, so I'll have 1/4. I can say that the sine of alpha is equal to plus or minus the square root of 1 over 4, which is equal to plus or minus 1/2. Now, the sine is equal to 1/2 at pi over 6. It's also equal to 1/2 at 5 pi over 6, 7 pi over 6, and 11 pi over 6. And again, anything bigger than pi over 2 is going to give me a right angle. So the only value that is going to make sense as an optimization is going to be alpha equal to pi over 6. That has to optimize this particular problem. Now, if we go back to the area equation that we came up with right here, let me copy and paste this. So let's copy that. All right, so let's plug in pi over 6. That'll give me 144. And so it'll be the cosine of pi over 6 to the 4th times the tangent of pi over 6. Okay, we can do that. The cosine of pi over 6, I've got 144. The cosine of pi over 6 is square root of 3 all over 2. And we need to raise that to the 4th power. The tangent of pi over 6, well, tangent is the sine of alpha over the cosine of alpha. And so if I do pi over 6 and the cosine of pi over 6, I'll get 1/2 over square root of 3 over 2. That'll give me square root of 3 over 3. All right. So 144. And then the square root of 3 to the 4th power will give me 9. 2 to the 4th power will give me 16. And then I'll have square root of 3 over 3. All right, so I can cancel out a 3 here. Cancel out a 3. I'll have a 3 there. And then 144 over 16, those cancel. And if you go 144 divided by 16, you end up with 9. And then 9, and so I got 9 times 3 times the square root of 3 ends up being 27 square root of 3 units squared, which is, surprisingly, what I got when I did it the first time. So our answers match up. And that is a long lesson, and I know that, folks. So, the Star Wars fun fact of the day. Frank Oz is both a puppeteer and iconic voice of Yoda, but he got his start voicing many other childhood characters with Jim Henson and the Muppets way back in the 1970s, back when old Mr. McCulley was born. And some of his other fan favorites were Grover, Miss Piggy, Animal, Fozzie the Bear, Cookie Monster, and Bert from Bert and Ernie fame. Well, that's all I got for today, folks. I know it's a long one. Have a good day. Bye.